In this video, I'm going to discuss a little bit further about forces, and we're going to go back and relearn how to do vectors and things like that. So we talked about how electric force is very similar to gravitational force in that it's a field force, and we learned that the equation for electrical force is Fe is equal to a constant, Q1 times Q2, the magnitude of the charges, divided by their distance apart squared. And also recall that the Coulomb's constant here it could also be written like this, where we have this weird little e sub naught, which is the permittivity of free space. Those two things, this and this, are interchangeable. Okay, so we're also going to talk today about multiple charges in a situation. So one of the things you got to point out is that electric force is very similar to gravitational force, but there is a difference. Gravitational force is always an attractive force, but electrical force can be both attractive and repulsive. Right? Attractive is if the charges are opposite of one another, and repulsive if they are the same, or they are like charges. So if we look at just a basic example, let's go ahead and take this example. Let's say I have a positive point charge here, and a negative here, and a negative here. Now we always put ourselves in the position of one of the charges. So if we want to know the force acting on the positive charge, then we have to think, okay, so which direction is this thing going to move as a result of this? Well, it's an attractive force, so it's going to move that way. So that would be the first force. And then you think, okay, well, what direction does it want to move as a result of that? And so this would be this direction. Okay, and because forces are vectors, you know, they would, you'd have some sort of resultant force that's sort of like in between, right? So this would be the resultant force. Okay. Now, let's say we had a situation like this. Let's say we had a positive and then a negative over here. So the force acting on this charge as a result of this one, this guy is making him want to go away, right? So that would be the direction of that force. And this one is pulling him in this direction, so that would be the direction of that force, and therefore the resultant would be, you know, in that direction. Okay, so we got to remember our ideas of vectors when we do these things. Okay, so I'm going to do an example, and this example, this is actually called superposition principle. I don't know why, but this whole idea of force being vectors and everything is called superposition. So we're going to just do an example where we actually have this scenario. Okay, so now I'm going to give my charges an actual value, right? So here, let's say this charge is a positive 2 microcoulombs, and then the negative charge, so I'm kind of doing this scenario up here. The negative charge that's over here is a negative 3 microcoulombs. Okay, and we'll say their distance apart here is going to be 0.2 meters. Okay, and then down here I've got another negative charge, same distance. We'll say 0.2 meters again, but in this case this charge is a little bit stronger. It's negative 4 microcoulombs. Okay. So we just need to calculate force 1. We remember up here from our picture, you can see that, well, the first force is going to be in this direction, force 1. And then we have this direction here, this force would be force 2. So force 1, we're going to calculate it. So force electric 1, I'll say, is equal to K, which, remember, K is the Coulomb's constant, which is 9 times 10 to the 9th. Okay, so remember, I'm just going to write that up here. Coulomb is 9 times 10 to the 9th. And then you have Q1, Q2, all over R squared. So the first electric force is going to be equal to 9 times 10 to the 9th times the charge, which is Q1. So we'll say this is Q1. And the prefix micro means times 10 to the negative 6. So this will be 2 times 10 to the negative 6 coulombs. And then the second is negative 3 times 10 to the negative 6 coulombs. And really, the negative is just going to help you to determine the direction. I just like to, you know, ignore negative and positive and use my vector method to figure out direction. Okay, and then all over the distance apart squared, so 0.2 squared. Okay, and if you punch that all into your calculator, you actually get that that's equivalent to 1.35 newtons. So right here it's 1.35 newtons. All right, now we need to find this vector. So again, we're going to write out the equation. So force electric 2, we'd say again is 9 times 10 to the 9th, 2 times 10 to the negative 6th. But now we have negative 4 times 10 to the negative 6 all over 0.2 squared. Okay, and if I plug that all into the calculator, I will get, let me see, I have it written down here somewhere, 1.8 newtons. Okay, so force 2 right here is 1.8 newtons. And that makes sense because remember that the magnitude of the force is relative to the strength of the charges. So here you've got 2 and 3, and here you've got 2 and 4. So it makes sense that this one's a little bit stronger. Okay, but now remember that we need to find the actual resultant force. Okay, so we're going to use our method, our tail to tip method. Remember? So you take the first vector. Here, let me just move this down a little bit. Okay, so we're going to take the first vector. Let me see so you can see it here. Okay, which is this. I'm just going to pick it up and I'm going to draw it here, and that's a magnitude of 1.35 newtons. And then I take the second vector and put it at the tail. Remember, tail to tip. So the second vector, actually, I can visually put right here, which is 1.8 newtons. And therefore, my resultant vector would be this. Okay? So in order to solve for this, I not only need to solve for the magnitude, but I also need to solve for the direction. So it's the hypotenuse of a right triangle, so we just use Pythagorean theorem to figure out what it is. So 1.8 squared plus 1.35 squared, second square root, second answer, 2.25. Okay, so the resultant force, electric, is 2.25 newtons, but we not only have to put the magnitude, we also need a direction, so we just need to figure out what this angle is. And you know, we have all sorts of different, we've got all the sides, so we just need to figure out, we'd pick a trig function to use. And so I'm just going to do you know, opposite over adjacent, do tangent. So 1.8 over 1.3, and then do tangent to the negative 1, and that will give me the angle. Making sure that my calculators in degrees. I know it's been kind of a while since we've done this, and I know a lot of you are in calculus, so just make sure that you do that. And then second tangent, second answer. I get about 53 degrees below the positive axis. Okay? So, again, it will be a good review of doing force vectors, and one of the major tricks to it is, you know, starting with this, starting with drawing the picture. And if you've got a lot of charges around, just always remember you're putting yourself in this guy's position, in this this charge's position, and think which direction is he going to move as a result of the other charges.